Hello everyone, we are from Suppression Process 2, Group 2L. We'll be presenting on our integrated design project titled Hollow Fiber Membranes for Removal of Contaminants from the Raw Natural Gas. I am Arina Azwa and will be presenting on the introduction as well as the flux and membrane selectivity.
As you can see, based on this pie chart, the total natural gas demand by end use as of August 2019 are leading by the electric power and industrial field. Natural gas has been a popular energy source for many decades, and the demand is continuously increasing worldwide. However, the raw natural gas consists of the amount of methane and other components such as higher hydrocarbons, water, acidic gases which are carbon dioxide and hydrogen sulfide, and other impurities such as helium and nitrogen. Looking into the acidic gases contained, which are hydrogen sulfide and carbon dioxide, which have been the major impurities in the industrial gas mixtures. The presence of CO2 reduces the energy efficiency of natural gas, and it is one of the top contributors to the global warming. H2S, on the other hand, is a highly toxic and corrosive gas. The existence of these acid gases, CO2 and H2S, in the natural gas increases the risk associated with the gas plant and requires the usage of special materials that are able to withstand the corrosive equipment. Hence, in this project, we are focusing in designing a membrane separation process system to remove the contaminants from the raw natural gas in stage 1 according to the given operating conditions and composition.
Hi everyone, my name is Jessa and I will be presenting the overall and component molar balances for this project. First and foremost is the overall block diagram of our membrane separation process. We were tasked with the removal of three main impurities, which are hydrogen sulfide, carbon dioxide and water. For this very task, we have decided to go with the three membrane setup for maximum efficiency. Hydrogen sulfide is to be removed first due to its corrosive nature, followed by carbon dioxide and lastly water. Notice that how in each membrane a little bit of CH4 has been assumed to be permeated as well. Moving on, we have the given conditions at the inlet and our desired conditions for the outlet according to the given acceptable range. For the inlet conditions, it was a matter of converting the composition of constituents from weight percent terms into terms of mole, while for the outlet, a midpoint was chosen from the given acceptable range before then converting said midpoint value into terms of mole. The reason for converting the composition into terms of mole will be depicted later on in the presentation. Next, our entire membrane separation process is depicted here. This diagram shows the given inlet conditions as well as the desired outlet conditions within the acceptable range. As mentioned before, a small amount of methane is assumed to be lost due to no process ever being 100% efficient, and in this case, 10% of methane is assumed to be lost. By factoring in that loss, the number of mole of methane lost to the permeate stream in total can be calculated, as can the number of mole remaining in the retentate. Once that is done, the individual mole fraction of the constituents desired at the outlet is multiplied with their respective molecular weights to obtain the total molecular weight, which is then used to divide an assumed output of 1000 kg an hour. Next, with the availability of the retentate molar flow rate as well as the fraction of methane in the retentate, the flow rate of methane can be calculated and then used to determine the total molar flow rate of the inlet. Once the inlet flow rate has been determined, it's a matter of simple overall molar balance to determine the total molar flow rate of the permeate stream, and when that is done, a component balance is carried out to determine the final fraction of components in the permeate stream. Moving on to the first membrane unit, which will be removing hydrogen sulfide, the molar flow rate of the component in the permeate stream is determined first, and in this case, the molar flow rate of hydrogen sulfide followed by the permeated molar flow rate of methane before summing it up to obtain the total molar flow rate of the permeate stream. The individual molar flow rates are then divided by the total molar flow rate to obtain the fraction of components in the stream. The molar flow rate of the retentate stream is then calculated with the availability of the feed and permeate molar flow rates, and upon completion, component balance is used to determine the composition of components in the retentate stream. The second membrane unit is tasked with removing carbon dioxide from the feed stream, which is the retentate stream from the first unit membrane. Similar to the previous membrane unit, the molar flow rate of the main component in the permeate stream is determined first, and in this case it is carbon dioxide followed by methane. The individual molar flow rate are summed up to get the molar flow rate of the permeate stream, and overall molar balance is then carried out to determine the molar flow rate of the retentate stream before carrying out component balance to determine the composition of components in the retentate stream. Lastly, The third membrane is used to dry the natural gas stream. In this case, the retentive stream has already been established when the overall membrane separation process was depicted at the beginning of the presentation, and the retentive stream from the previous membrane is used as the feed stream for this membrane. With the available values, the molar flow rate of the permeate stream can be calculated, and the composition of the permeate stream can be calculated via component balance. That's all from me for the presentation of the molar balances for our proposed process. I would now like to pass the presentation to Amir.
Hello, my name is Muhammad Amir Ali with ID number of 23770. Firstly, I will present about the membrane material, type and configuration. So, the properties of membrane module are obtained from the journal, which is from Fendersky 2017 and George et al. From 2016. And in the table, we will show about the process condition of our membrane and a membrane module. Okay, next is to determine the dimension of each membrane unit. So there are 3 membrane units in our project, which is for primary, secondary, and tertiary. So we are taking the membrane area as 15,070 meter square, while we're taking the shell membrane module volume of 20,000 meter cube. This is we are taken from the journal. So allow 20% of total space for good flow distribution. So meaning that in a cylindrical vessel, there are 20% of space are need to be free, whereas to give the good flow distribution. So 20,000 meter cube divided by 0.8 will give the 25,000 meter cube. And then we're assuming the ratio of 4 to the 1 cylindrical. So volume, the formula of volume will get the pi dt squared LV over 4. Okay, next is our membrane configuration. Okay, as you can see in this table, there are 3 type of our membrane, which is primary, secondary, and tertiary. So the configuration for the 3 membrane are the same, which is the hollow fiber, while the flow is also same, which is uniform and not dead region. So the material used for the 3 membrane is the cellulose acetate. And why we choose cellulose acetate? Because it's easy to clean and also easy to get maintenance. So our shape for membrane module is a cylindrical vessel, and mode of our operation is a single flow, while the packing density inside our hollow fiber is a medium packing density. So the material for the tertiary membrane module is a cellulose acetate, have many intrinsic properties such as excellent mechanical strength, biocompatibility, hydrophilicity to attract more water inside it, good relative thermostabilizing, and high suction capacity. This is from our journal, which is from Figoli 2015. So besides that, hollow fiber configuration of the module with the medium packing density is better choice in this particular sector, as the typical major drawback for hollow fiber membrane is the pressure drop inside the membrane module, and it will affect the efficiency of the permeation of volatile permeate. Okay, lastly is our schematic drawing of the membrane and membrane module. Okay, as you can see from the left side is the front view of our membrane module, which is a cylindrical vessel, while the right side is a side view of our cylindrical vessel. So as you can see here, there are this is the tangent to tangent length dimension for our cylindrical vessel, while the diameter is stated here, which is the 19.96.
So for as the flux of each membranes are calculated based on the formula of volumetric flow rate divided with membrane area, which in the video I am displaying the calculation for the first membrane unit, which is for the H2S removal. The membrane area was set to 15,070 meters squared as per reference, and the total flux calculated for the first membrane unit is 1.17 exponent -4 meter cube per meter squared hour, and it followed by the second and third membrane flux values calculated and shown in the table here. As for the membrane selectivity, we are using the formula of the ratio of the permeability coefficient of the components, and it was being calculated for each membrane units as to determine the components that will be concentrated in the pyramid stream. The permeability coefficients for each component are based on the material chosen for the membranes, which is cellulose acetate. Based on the above results, cellulose acetate membranes are more permeable to CO2 and H2S comparing to CH4 and other hydrocarbons. It results in the higher concentration of CO2 and H2S in the pyramid stream, whereas the CH4 and other hydrocarbons will be concentrated in the retentate. This can be seen in the material balance and component balance, which has been done by my groupmate earlier. This can be seen in the outlet compositions of each of the membrane units, which has been presented by my friend earlier in the mass balance part. That is all from us. Thank you.